Additive inverses. So we're actually going to do something now that allows us to discontinue distinguishing between negative v and minus 1 times v. So just to clarify, we use negative v to indicate the additive inverse of v. So in other words, the thing that you add to v to get back to 0. And we use minus 1 times v for the scalar multiple of v by the scalar minus 1 from our field. And since we know that our field always contains 1 and it's closed under additive inverses, we also know that it contains minus 1. So there's nothing there that isn't automatic. But what we need to show is that these two things are actually the same. Okay, so we'll make that our proposition. Negative 1 times v is secretly the same as minus v. Okay, let's prove that sucker. So, well, what we're going to do is we're going to show that if we add the scalar multiple, then we get 0. And then by uniqueness, that'll give it to us. So let's see. So first off, I can use the multiplicative identity property to make a 1 appear in front of the first v. Here, I'll make that a fancy one. There's a fancy one. Okay. And so my justification here is I'm using the multiplicative identity property. And that's, well, I guess it's redundant to say that it's in the field because you can't multiply vectors, but oh well. Okay, so now I can use distributivity in reverse to collect the 1 and the minus 1 together as coefficients of the vector v. So that follows by distributivity. And so basically what I've done now is I've made it so that we're looking at subtracting 1 and adding negative 1 in the field being the same thing, and using that as our justification. And so if I do 1 minus 1 now, I get 0 times v. And so this is using the additive inverse property in the field. And then we just saw in the previous clip, tale of two zeros, that that's actually equal to 0. And then I'm done. So my justification for that last step there is some previous result.